So up next, we've got Paul McKenney from the Linux Technology Center, IBM's Linux Technology Center, and he's talking about real-time response on multi-core systems. On to you, Paul.
Thank you. So one of the things that's shown up recently, recently by my standards in Linux, is the idea of having real-time in mainline. And this has been something that's taken a little bit of time to show up. It was in 2004 that I first realized that RCU needed some help in order to get real-time response, and we went through a bunch of stuff I'm not going to go through, but probably the most recent thing was getting RCU priority boosting in mainline. In other words, a way of preventing starvation of readers by high priority real-time processes. So, I was feeling pretty good about this, getting things pretty much there. And it's actually been in production for a long time in the form of the real-time patch set, of course, before it went mainline. In fact, IBM actually was partnering with some people shipping aggressive real-time on 64-bit x86 systems. And we're down to like 20 microseconds, maybe 40 microseconds scheduling latency on these things, which, is not too bad. Of course, there's just a huge number of people that did that. I just did the RCU part. And of course, there's a huge number of people outside of the kernel in the distros and other places that help make this happen. And of course, we have to thank Linus for putting up with us, sometimes more gracefully than others, but there we are. The funny thing was, even in 2007, there were a lot of people that just weren't inclined to believe that something like real-time in Linux could possibly work. They were of the mind that if you wanted to do real-time, you had to have a special purpose-written operating system that was designed strictly for real-time and nothing else. And demonstrating Linux could do this didn't really seem to change their beliefs much. So I decided to do a write-up, which appeared in Linux Journal in 2007. And I mean, it had nice cute cartoons, There are people complaining about that it couldn't possibly be hard real-time. And of course, if you show me a hard real-time system, I can show you a hammer that will make it miss its deadlines. And it's possible. You could go and make a much more robust system. You could ruggedize it, you could use redundancy, clustering, and things like that, but I can get a bigger hammer. Of course, some people objected to this, saying that, look, we're talking about real-time software here. And if the hardware blows up, it's not the software's fault. You can't go around knocking the software because the hardware is bad. I'm not sure I'd consider it bad if I hit it with a hammer and it broke, but okay. And the thing is that what really happens is real-time is a function of the system. Imagine this poor guy, his life depends on this machine back there, and it has to have real-time response. And the orderly comes up and says, "Rest assured, sir, that should there be a failure, it will not be due to software." This might not be as reassuring to him as he would like. And in the article, I called out 5 real-time myths that I felt no longer held. But despite all the cute cartoons and everything, the message wasn't all that well received at the time. At least not by everybody. Nevertheless, about 6 years later, I really feel that it stood the test of time. That a lot of these things have actually worked out. We have Linux running real-time in a number of different things, everything from laser welders to control of trains even in Germany, which wouldn't be the first place you'd expect to do that, but there you are. And any number of other applications as well. But I have to confess that I made one really big error in that article. And that error is what this talks about. So I didn't learn of the error until about a year ago. I got this email from Dmitry, whose last name I can't pronounce, and he reported getting 200 microsecond latency blows when RCU did grace period initialization. I wasn't really inclined to believe this. As we saw on a previous slide, we were getting 40 microseconds for all of Linux, of which RCU is a small fraction. And here he's telling me he's getting 200 out of just RCU. So my first response was, well, you gotta be kidding me. Fortunately, I kept reading the email, and it turned out there was one kernel configuration parameter that completely explained the difference. NR CPUs equals 4096. At which point, as you can see, my response was, you mean it only took 200 microseconds? RCU's got to basically do something for every group of CPUs. You have that many of them, and it takes a lot. And the thing was, it wasn't just that it wasn't like he'd made an error in the build process. He really had 4,096 CPUs on the machine, okay? So that was my big error. When I wrote that article, I was thinking that, I was being really out there over the horizon saying that real-time systems might have more than one CPU. I was thinking maybe, 4 or 8, maybe someday 16 or 32. And as you can see, I was more than 2 orders of magnitude small. I simply wasn't thinking large enough. And here's what was happening. You don't have to understand RCU very much for this, but it's code and data structures, and you have to do stuff with the data structures. So for this situation, each flavor of RCU, and let's ignore the fact there are multiple flavors, has an RCU state structure. And this kind of contains the global state of the current RCU grace period. We've had problems with lock contention. I mean, the same group of people filed a bug report in 2004 complaining about scalability on a 512 CPU machine. And so in response to that, I ended up making a combining tree, which is shown here, these RCU node structures, so that each CPU is assigned a leaf in this tree. And by default, there's 16 CPUs per leaf. And that means that the lock contention is kept down at a low level no matter how many CPUs you have. So in this case, 0 through 15 contend for a lock in just that one structure over there, where 4080 through 4095 are over here. And then the last CPU to respond to the current grace period, and only the last CPU, goes up to the next level. Well, if you have 4,096 CPUs, the first level, it's the root, so it has one of these structures and only one. Fair enough. The next level down has 4 of them, and the leaf level has 256 of them, 4,096 divided by 16, for a total of 261 RCU nodes. Now that particular hardware, a cache miss, can consume about 2 microseconds. So that was why I was surprised about only 200, because if I take that multiplied by 2, I end up with over 500. But who knows? What was happening was only 200. Okay, well, and part of the problem we have here is that it's not just that it has to go and initialize all that. What's going to happen every time you start a grace period is going to traverse that tree and initialize each of those 261 RCU node structures for the new grace period, with interrupts disabled. And, if you've only got, 4 nodes, and 4 nodes cover 64 CPUs, going and initializing these little structures, all 5 of them in that case, with interrupts disabled, this is not a problem. When you have 261 of them, well, that's a different story. Now, the thing is that one thing would be, okay, fine, just don't disable interrupts. Well, you can do that, except that as soon as you enable interrupts, or enable preemption, and for the real-time guys, you have to have preemption enabled, not just interrupts. You're going up this tree and your CPU 4095, and you acquire the lock, and all of a sudden you're CPU 15. And that isn't particularly something that the current RCU initialization is prepared to deal with. So hence the interrupt disabling. In addition, when you're halfway through initializing this thing, if you have an interrupt that comes in and it says, oh great, we have an RCU update, let's post a callback. What grace period is it again? That might not be what you want either. One question, of course, is who cares? These things are huge. It's not like there's a large number of 4,096 CPU machines in the world. I don't know how many there are, but probably, you probably could count them and have fingers and toes left over. Well, their users, of course, care about them, as they let me know quite vociferously, actually. And actually, we all need to care about them. So one thing, if you look back through IBM's history about the 50s, I think it was Thomas Watson Sr. that was reluctant to invest in computers because he saw a market for maybe 5 of them. He figured that in the US there might be one for the East Coast, one for the West Coast, and maybe one for the Midwest, and there may be 2 other ones somewhere else in the world. And, well, 4,096 CPUs is a lot of CPUs, but I remember some conferences like this where people were upset at having 8 CPUs. And that's only 10 years ago. So we can't just ignore this. It may come at us faster than we would like. And the CPUs, the thing is that there's smartphones now, as we've heard several times in this conference, that are multi-CPU. And the other thing is, these guys are crazy enough to test crazy software. I mean, they were having this problem and they were willing to do stuff. And so if we give them advanced techniques, they'll actually get some of the bugs worked out so that by the time all of us need it, it might have half a chance of working. The other reason is that there are Linux distributions that build by default with NR CPUs equals 4096. I'm not making this up. They really do. All right? And I think it's something about them wanting to only have one binary, so to limit their testing. I'm not sure how they square that with what we do afterwards, which is to say, how many CPUs are there really? We'll forget about what the compiler said. And in fact, yeah, that happens. So RCU is going to have to adjust. And one way it could adjust, I mean, if you remember, I said there were 16 CPUs for each of those leaf RCU nodes. And if you're on a 64-bit system, and all the systems I know of that have 4,096 CPUs are 64-bit, you can get 64 CPUs in a bit mass, so why not just have 64 CPUs for each of the leaf nodes? And if you do that, things get a lot better. At this point, we only have to have 2 levels in the tree instead of 3, and we have 1 in the top as always. We only need 64 of them in the Lex node, and that's a total of 65 of these things, which is about a factor of 4 reduction in the latency. And in fact, it decreased the latency from more than 200 microseconds down to 60 to 70 when they tested it. And their users claimed this was barely acceptable, although I'm not sure you get any better of a compliment out of them than that, but at least it was something they could sort of live with. And that was a fairly easy change. It was just a matter of changing the config setup and having them build their kernels appropriately. I also made it so it was a boot time parameter so the distros could just have one binary, never mind the fact that I was giving as much trouble to them at boot time as they would have had at compile time, but okay. Unfortunately, we end up with round 1 of scalability versus energy efficiency. The problem is that the huge systems want 64 CPUs on each of those root nodes. And the smaller energy efficient systems want scheduling clock interrupts to be delivered to the system simultaneously, like at exactly the same time. And if all 64 CPUs attempt to acquire RCU nodes lock at the same time, it's not going to be pretty. In fact, we had something like that on their big system once, and it basically just hung the system. The lock contention was so horrible. All right, so what ended up happening, what's going on here? Let's say you've got a 6 CPU package with a single power domain, which I think is what I think they're building their system out of blocks like this, but I don't know for sure. Now on the top, this is what the kernel currently does by default. It's going to deliver the scheduling clock interrupt to all 6 CPUs at the same time. And what that means is you power the package up once, take the scheduling clock interrupts, then power it down. Now, once upon a time, the kernel worked differently. What it would do is it would actually skew the scheduling clock interrupts, so they would occur on different CPUs at different times. And you'd get something like this bottom graph here, where we get a spike of power consumption for the first CPU in the package, and then the second CPU in the package, and so on. Now that's great for lock contention because you only have one CPU going for the lock at a time, but it really sucks for power consumption because you turn this package on 6 times instead of just once.
Can you spread them out across different nodes?
Can I do what now?
Rather than having them all adjacent to the same RCU state, can you move them so they're spread out?
So can I move them so they're spread out so that, let me try to echo back what I think you're thinking and see if I understand your question. So what we're doing is right now is by default, all 6 of those guys be hooked into the same RCU node. And of course, that means if they get the scheduling clock at the same time, interrupt at the same time, they'll all power up and go for the lock at the same time. And so if I understand you correctly, what you'd like to do is we got 64 of these stupid RCU node structures, so take the first CPU and throw it on the first one, take the second one, throw it on the second one, and kind of just interleave across all these things. And there's a couple of, in principle, actually it's not a bad idea, it's a good idea, in principle that would work, but there's two practical problems with it. One of them is that, as near as I can tell, they put the stupid scheduling clock interrupts across the whole system at the same time, which, I don't know. You can actually make a case for that if you have a mostly idle system and it's got multiple packages. You have to power other things in the system up to power the packages up, in principle anyway. And so hitting them all at the same time, in theory, means you aren't powering up the ancillary circuitry unnecessarily. The other thing is that if I do that, I'm getting cache thrashing, right? Because I've got different CPUs from different parts of the system going for the same RCU node, which means it's thrashing back and forth across a large chunk of the system. Of course, the Intel CPU numbering does that for you anyway. I never have managed to have a meeting of the minds with the Intel guys about how that should work, but I don't know what to say on that. They keep telling me that I should make RCU deal with it and understand where the CPUs are and put the ones that are close together in the same package. On the other hand, Linus just told me off this morning for RCU being too complicated, so I think I'll take Linus's suggestion over theirs. All right, so we have our problem again in yellow there, and what Mike Galbraith did is he added a boot parameter controlling the scheduling clock interrupt skew. And what that means at boot time, you can choose whether you want your scheduling clock interrupts to happen all at the same time for maximum energy efficiency, or be spread out so that you can reduce the lock contention. And later on, Frederick Wesbecker has a patch that should reduce the number of scheduling clock interrupts altogether. If you have an HPC style situation, which is what these systems tend to run, if you have a single runnable task on a given CPU running in user mode, what his work will do, and it's getting close, I think hopefully we'll get there soon, what it would do is disable the scheduling clock interrupt while you were in that state. And the reason is that the whole point of the scheduling clock interrupt, or the historical purpose of it, is you want to wake the CPU up and look and say, hey, should I be doing something other than what I'm doing right now? But if there's only one runnable task in user mode, what the heck else are you going to do, right? So why bother asking? And that would, of course, reduce the number of scheduling clock interrupts and reduce the contention. What would happen, the way that works, there's some hooks in RCU that Frederick and I have been working on, so that when the CPU is in that state, RCU just ignores it completely. And therefore, its RCU node is just kind of doesn't do anything, or doesn't play with it, and things work there. Longer term, I hope what's going to happen is something similar to what Robert suggested earlier. It'd be kind of cool if they could just hit the scheduling clock interrupts, get them set up so that they offset them by just a little bit, possibly kind of round robining them. So you get a scheduling clock interrupt on one CPU and it passes it off to the next one. So you power it up for just a little bit of time, but make sure you're reducing the contention, and possibly having a couple of those chaining through the system to get it done. Yeah, Ben?
Yeah, because I expect that a lot of your energy costs come from active powering up, and so by simply passing it along, and you will be up for a longer period, but you will have less transitions. And the transitions are probably at least as costly as the fact that's there now.
And it makes sense to me. What Ben said was that the powering it up and the powering it down was expensive, really. I mean, that consumes a lot of time, and the scheduling clock interrupts are very small. So just kind of having them go sequentially within that window, it makes sense to me. But
using IPRs, you could get it close to one, and then when it's finished processing, it IPRs the other one.
yeah, I think that'd be great. And if you had a large enough system, you could, a really big system, you might be able to run several of those in parallel if you knew that the CPUs were far enough apart that they wouldn't be interfering much, but that might be something one does later as a further optimization. So hopefully something like that can work to make things automatic and just work out nicely so that the same code works on a energy efficient system and on a really big HPC system. Unfortunately, this had some unintended consequences. Then again, what doesn't? You see, the RCU polls CPUs to learn which are in dynamic idle mode. In other words, if a CPU is idle, RCU knows that it's not going to be doing any reading, and therefore it doesn't expect it to respond. It just sort of responds on its behalf. Well, this guy's idle, so I'll mark him as being done for him so he doesn't have to wake up. And what happens, the way that happens, is that RCU starts a grace period, waits for a few ticks, and then goes, if the grace period hasn't ended, it goes and looks at the CPUs and says, well, have these guys not responded because they're in dynamic idle mode or they're offline or what? So it goes across there. And what happens is that each CPU that is active and doing a scheduling clock interrupt could decide at any time, hey, it's time to do this forced quiescent state. We've waited too long. Now, if you only have a few CPUs, like only 100 or so, the odds of any large number of them doing it at the same time is kind of small. We have 4096. The clock suddenly rolls over and it's time to go and scan, and maybe only 500 of them decide, yeah, let's scan. And that means they all go for this lock. It's a tri-lock, so it's not a contention problem, but it's a memory contention problem. And this, again, causes massive memory contention and results in a system hang on this large of a system. There was an intermediate solution. Dmitry Svinik rearranged the fields in the RCU state structure, and that reduced the memory contention enough, or kind of spread it enough, that it allowed the system not to hang. And he also forced a longer delay between forced quiescent state invocations, but those seemed, yes, Ben?
Can't you introduce fuzz in the delay?
Don't you reduce?
And can you introduce fuzz in the delay?
Okay, that would be one possibility.
CPU number through the LSR style, so the random stuff.
There's two things. I didn't think of that, and I thought of something I think might work better, but you judge for yourself when we get a few slides in. But that would have been one thing that we potentially could have done, would have been to add the CPU number. Oh, the reason I didn't think of that was that the delay is only like 3 ticks, and it's on jiffy boundary.
It doesn't have to be very long to avoid the cache line problems.
Mm-hmm.
So you can do a microsecond or so, it's probably going to be enough to avoid contention.
So okay, I'll talk to you offline on how to implement that.
Yeah, I don't know the structure of the code well enough.
Yeah, it just compares the jiffy counter. So, but anyway, the suggestion for the benefit of the tape is to make it so that the CPUs kind of fuzz the delay. So instead of add exactly 3 jiffies, CPU 0 might do exactly 3 jiffies, CPU 1 might do 3 jiffies in a microsecond or so, and so on, so they aren't all diving in at the same time. And I don't know if that will work here, but it's a really good technique in general. It is very applicable, and it's a good idea. Okay, but what we ended up with is another fight between scalability and grace period latency. I get beat up fairly often for people that want the grace periods to go faster. And also, these guys clearly were beating me up about making good real-time response for very large systems. So the problem is that increasing the polling interval, which is what Dmitry did, increases the expected grace period delay. And they were complaining about it being too long, so that worked for him, and that's fine, it's a good workaround for him, but I can't put that in mainline. So short term, what I did is I just made that parameter, instead of having to rebuild the kernel, it's yet another boot parameter, or you can also change it in sysfs at runtime if you want to, and people can choose what works. Of course, at some point, there was a time when people added kernel parameters and people were happy with that. And then people got upset and wanted single binaries. I'm sure that the day is coming when people are going to get upset about how many boot parameters there are. So I'd like it to work automatically so that if you do have to mess with boot parameter, it's the uncommon case. Longer term, the idea is, this is what I did, Ben, instead of fuzzing the stuff, is to move the grace period startup, polling, and polling being the forced quiescent state, into a K-thread, which meant that instead of all the CPUs being responsible for saying, hey, it's time to go poll the CPUs, just as one kernel thread was. And that, well, it didn't eliminate, it eliminated the lock, but that also had some unintended consequences, because RCU has some energy conservation stuff where if it enters idle, it tries to force the RCU grace periods to go through so it can shut off the scheduling clock tick. And in doing that, it tries to force quiescent state. So if you have a whole pile of CPUs out of 4096, there might only be 500 of them. Trying to enter idle at the same time, they're all going to be pounding on forced quiescent state again. So the K-thread doesn't come for free either. This increases the binding between RCU and the scheduler, increases the dependencies between them. And what happens is that this K-thread has you wake it up, and of course the event, the thing you wake it up with has a lock, and that's a single lock. And so there's some potential, so you have to worry about contention there. On the other hand, we can put explicit preemption points in at this point. Now we have it in a single K-thread, so we don't have all these weird dependencies about other CPUs doing things while we're doing things, just as K-thread is initializing it. And at that point, we can reduce the contention, or the preemption, reduce the scheduling latency, I'll get the right thing sooner or later, down to something negligible.
Don't you need to hack the shell? Because I can imagine you going to idle, you trigger the, sorry, I can imagine you trying to go to idle, you trigger that thing, and the scheduler will begin, say, you on CPU A, I'm going to trigger that thread on CPU A.
Yep.
And so it immediately takes you back out of idle in order to run your K-thread.
Yep.
So that doesn't look very good to me.
Okay, that could happen. So let me make sure I understand your concern. So you got this system that's mostly idle, and the K-thread decides where it wants to run, it might run anywhere. And so it decides to run on a CPU that has no business running anything because you want it powered off because you want this whole package to be powered down for power savings, energy savings, right? And RCU can't know about that really, because it doesn't really know what you want, nor does it know what the CPUs are, but there is a K-thread there, and if you want, you can pin it to whatever CPU or set of CPUs you want, no problem. So if you have a particular situation, maybe you got an HPC application, this K-thread might be one you'd want to put on the CPU that's used for monitoring or whatever else, and just not let it go over where the worker threads are. But again, that's something that the people running the system have to decide. I don't know what they want or what's appropriate in general. Does that make sense, or did I miss the point of the question?
It does make sense. It's not exactly what I had in mind. I was thinking more about, scheduler decided there's nothing to run anymore on this thing. Wants to go idle, triggers the K-thread on that same CPU, and it can't go idle anymore, got into the K-thread. K-thread does a job, goes idle, want to trigger RCU again.
That can happen anyway. I mean, that can happen if I'm trying to go idle. I mean, we can be trying to take the CPU idle, and somebody wakes something up on that CPU.
Sure.
So we have to handle all that stuff anyway.
RCU is causing the act of going idle to trigger more work on the same CPU that is trying to go idle.
Right. So.
And I'm curious whether you have measured the effect of that.
Well, a little bit ahead. What I'm trying to do actually is eliminate that effect entirely. But
that will require getting even more tied into the scheduler.
One of the problems with having RCU stuff in K-threads, it's nicer having it in soft IRQ because you can do a raised soft IRQ almost anywhere. In the common case, it just sets a bit in a per CPU variable. You do a wake up and you got to grab a lock, you got to disable interrupts, you got to do this, that, and the other thing. And if you got called from the scheduler, which RCU does get used from the scheduler, that might not be a winning strategy. And it can be fun. Anyway, I believe that if I do the math and do the linear extrapolation, I believe this would take them from 200 to about 70 microseconds. That was the first part. We measured the first part from 200 to 70. And I believe that putting the preemption points in and moving to a K-thread would get them down to about 30 microseconds, although I haven't tested it, which of course would probably raise the question in a number of your minds, why not just test this? And the reason is because I don't happen to have a 4096 CPU system. But I do have a long history of relevant experience to this situation. You see, I used to do computing with these things. And the way this worked, you got this key punch and you punch these cards and you get the stack of cards. You put a rubber band around it and do a bunch of things to avoid messing it up if you drop it. You drop them and get out of order, you have to sort them yourself. And then you hand the deck to these people behind this glass window, and they run it through the machine, and sometimes later they give you a printout and the deck back if you were lucky. And that sometime later, if you did things right, and use the computer during dinner time or late at night or some other time when people weren't using it, you got it back within minutes. But if you waited till like the end of the term, or you're trying to do it another time, it might be hours or even days before you got your deck back. And so I've had some experience where you make a change and then get your test results back sometime later, although they're actually pushing the limits of, they may be getting a record. In any case, they did try running it once and had some configuration problem. If you have a machine that big, it's very expensive and it's almost never idle. And so you have to schedule time and a long time ahead. And I think what happened is getting it down to 60 or 70 microseconds got to where their customers were screaming to them about something else. And so it's down to the point where they aren't testing it readily. But we still have the single global lock. And it's the thing that when you're doing forced quiescent state, you only need one thing forcing quiescent state at the same time, and only need one thing waking the thread up at the same time. And wake up uses a lock on the wake up. So if 500 CPUs try to wake the same thread up at the same time, it's just as bad as all of them going for a global lock. But, and the thing is, you only need one of them to succeed, right? If you have 500 people at the time trying to wake this guy up, you only need to wake him up once. And everybody else that fails, just want them to, you want the people that lose to lose as quickly as possible and get back to what they were doing. In some sense, winning is losing, because if you win, you have to go wake the guy up. And if you lose, you can just immediately go back to what you're doing. And this can be handled by something, a variant of a tournament lock. And Grocki and Thacker did a publication 23 years ago on that. But we avoid some of the, they did not like that lock, it sucked. Okay, because they had kind of a tree, and if you had a busy part of the tree and an idle part of the tree, the guys in the idle part of the tree got the lock really quickly, and the guys over here had to wait behind each other. But we don't really wait, see? So what you do is you put the locks in this RCU structure tree. So what happens is you're going to wake the guy up. So you go for a lock in the leaf RCU node. You do a tri-lock. If you fail, you win. You get to go off and do something else. If you acquire the lock, that means that nobody else on this corresponding to the structure is going to do it, so it's up to you. So you check to see if it's been done already. There's a flag you check. And you go up to the next level and try again. If you make it all the way to the top, then you're the guy that needs to wake him up. Okay? And at each stage you have to release the lock of the guy you just let go of, but you need to acquire the next lock up before releasing the other one, otherwise you end up with people passing each other up the tree, which I didn't want to deal with. So again, at each level what you do is you check this GP flags variable. If the GP flags field in the RCU state structure is set already, you know somebody else already woke them up, there's no point in doing it again. Otherwise, you try to get the lock at the next RCU node up the tree. If you fail, then somebody else has the lock and they're the ones waking him up. If you succeed, you keep going up the tree. Get to the top and the flag's in the set, you do the wake up and you set the flag. And it's pretty straightforward. It's just a few lines of code there. Just a loop going up the tree, check the flags and acquire the lock, release the old one and keep going. The actual effectiveness is TBD. Again, test time is difficult, but in my testing and modeling, it seemed to work quite well.
Do you get cache ping pong?
Cache ping pong? You can. On the other hand, what we're getting is a limited cache ping pong. The guys that lose only go once, right? Whereas if you had a pure lock, they would fight and keep fighting each other until all of them got the lock.
It depends on the implementation of trial. If it's an LLSC kind of implementation, it might people just try to do the atomic operation for the trial.
If I'm not too confused, well, we'll have to take a look at that. In this case, it'd be fine with me if, no, you're right, because I have to see that the lock is held by somebody. But that means if I pick it up, if I pick the thing up, then I see that it's held, then we leave. It's only if I pick it up and it's not held that we might have ping ponging. Or am I confused about how it works?
Yeah, if you
Implementation of tri-lock is based on load store conditional.
Right.
You might have a whole bunch of people who see it not taken and try to actually store condition at the same time, and not all implementation guarantee that one of them going to succeed.
Oh, okay. Well, that could be more difficult.
So, yeah, you depend. It becomes very, very implementation specific. Your preference profile might depend a lot between Ampere or x86 here.
But it should work better than having all CPUs going after, unconditionally going after global lock, right? So you're right, but so what I'm doing here is I'm not making the problem disappear, but I'm dividing its problem by 4096 divided by 64. So you're right, there may be problems. On the other hand, if it's 64 systems causing that issue, then we may have to do something else. So there's some other possible issues. I'm not going to go through these in detail, but there's a number of things that could come up. One of the things that we're doing is I'm actually hoping to use callback numbering to make it so that the guys entering idle don't have to ever force quiescent state. And that should essentially eliminate contention on that lock. The next lock that would cause problems would be the guys that want to start a grace period. So I'd probably end up keeping the code and the data structure and just repurposing it for the initialization instead of the forced quiescent state. At some point, I may have to parallelize the initialization. Right now, I just have one guy go through all the structures. I heard some rumor about an even larger system out there somewhere. And if you get up into the, if you start pushing 100,000 CPUs, then it may be worthwhile to actually initialize them in parallel. But whatever. I'll worry about that when they complain about it, and we'll see how it goes. Most important, though, by putting in a K thread, as was noted earlier, we're actually increasing the binding between the scheduler and RCU. And the problem with this is if these guys get in a fight, they normally both lose. Okay, we really would rather have them both win, and the way they both win is not get in the fight in the first place. And the problem we have is that RCU uses a scheduler now, it wakes things up, and the scheduler has been using RCU for several years. And of course, that means you get deadlocks and all sorts of fun things. There was a Element article a year and a half or so ago talking about one particular case, and more recently we had some fun with the scheduler. Now I forgot what we had fun with, but you can check that and find out what fun we had. But the hope is that driving the grace periods should be okay, as long as the scheduler doesn't wait for the grace period on any of the wake up or context switch fast paths. I mean, it's okay for it to call RCU and have the thing go off, but it would be bad for it to actually wait for a grace period to complete. And of course, either directly or indirectly. I mean, if it grabbed a lock that was held, or a mutex that was held across a grace period, that would be just as bad as actually calling synchronous RCU. And also, another thing we can't have is we can't have a scheduler executing an RC retime critical section while holding a run queue or prior to inheritance lock if there was any time was preempted while you're in that state. In other words, let's see if I can get this right. In other words, if it started an RC retime critical section and it was preemptible at that point, and then it grabbed, for example, a run queue lock, which disables interrupts, and then it exited the retime critical section, that would deadlock. I think we're going to be helping LockDep find that sort of thing. One weird thing I didn't expect going into this is that putting in a K thread, assuming we avoid problems with schedulers, actually simplified RCU. And one of the things we had before is if you have all the CPUs entering dynamic idle mode, you can end up with a situation where a grace period needs to go ahead, but none of the CPUs is going to push it because they're all asleep. And so there was some tricky code to make it so that at least somebody would be there to make the thing happen. And we actually had some bugs where there'd be RCU stall warnings on really quiet on real quiet systems. This wasn't something you'd happen on a normal laptop. It was embedded systems that could go for minutes with absolutely nothing happening where this would happen, and it really did. But because we've got it in a K thread now, the K thread wakes up and things happen, regardless of what state the CPUs are in. So that's actually an advantage. Ben pointed out earlier that we can have problems if we have the K thread running on an inappropriate CPU we don't want to wake up. On the other hand, having that K thread means that we're going to wake up and push the grace period, regardless of what state the CPUs are in. So that actually simplified things quite a bit. In addition, there was a bunch of code in forced quiescent state, because you can end up with this thing where one CPU is trying to see if it can pull the dynamic idle CPUs, see if it can finish off the grace period, and then one of the things, the last CPU suddenly checks in, and it's busy trying to make a grace period complete that already completed, and that takes a bit of code to sort that out. In this case, that can't happen, because we have one K thread that's going to force the quiescent state, and it's not going to end the grace period until it's done forcing quiescent state, and a bunch of fairly complicated code just vanished because of that. So, it's not every day that you can make your code accommodate a really, really big CPU, a really, really big system, and actually simplify it as a result, but, we might be in that situation here. Okay, so they say the best way to predict the future is to invent it, and my experience is that that's not foolproof. And in isolation, S&P real-time and energy efficiency are well known. There's been people working on each of those separately for decades. I mean, they've been different people in different areas. And the real opportunities for new work and new cool stuff involve combinations of them. So it's kind of like plate tectonics, Each of these things is a plate, and the excitement happens where the plates come together. There appears to be some need for tens of microsecond latency on 4096 CPUs, which I certainly didn't predict. And I suspect what this means is that in a few years we'll have people running pretty heavy-duty real-time on tens or hundreds of CPUs. And the cool thing is that supporting this is actually not impossible. We should be able to make it happen with appropriate configuration and other limitations. It'll only require a little mind crushing. It's not totally impossible. There's a lot more work to be done in the Linux kernel, but for these combinations of things, I think that there's also a lot of work required in open source applications. We have a case where this kernel scales quite a bit better than most applications do, and so there's some work there. And the large system challenges seem to me to not to be in tweaking and rearranging cache lines. I mean, that can help. That's a good thing, and that's what you need to get the last little bit out. But most of it is in the design level, actually how your algorithms fit together. And the real surprise, sometimes taking on these crazy requirements actually ends up simplifying things. Doesn't always work that way, but this time it actually did. IBM Legal, as always, sponsors that slide. And we're near the end. Any questions?